Okay, so differentiating and integrating are not the only things that we can do. We can also substitute in for these series as well. So let's look back at sine of x. So our polynomial for sine of x, that infinite power series, is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Okay, so could we construct a Taylor series centered at 0, because that's what the original one is centered at 0, for sine of x squared? So things that we want to kind of remind ourselves of. If we take the first derivative, that would give us our first term. If we take the second derivative, that would give our second term, so on. So let's look at what that would look like to kind of help us out here. So if we were to do that, we would have f of x is equal to sine of x squared. F prime, which isn't too bad, would be sine of x, which is cosine of x, and it's of x squared because the inside stays the same because it's chain rule. And we're going to multiply by the derivative of x squared, which is 2x. So the derivative of this function, 2x times cosine of x squared, isn't that bad. But if we take the derivative again, which we would have to keep taking derivatives to find these coefficients to make a Taylor polynomial, we would get the derivative of 2x times cosine of x squared. Because there's that times, we need product rule. So we have the derivative of 2 times cosine of x squared plus the derivative of cosine of x squared, which is negative sine of x squared times 2x times the 2x from original. So u prime times v minus v, or plus v prime times u. This simplifies to 2 cosine of x squared minus 4x sine of x squared. Okay, you could keep taking derivatives, but each time you take a derivative, you're going to be adding more terms and adding on another product rule every time. So the more that we have to do these derivatives to find all the coefficients of these Taylor polynomials, the worse it gets. So the whole reason why we like substitution is because we want to use what we already know about these Taylor series, these power series, in order to make our lives a lot better. So we're going to try substituting instead. So let x equal t squared. And we want to look at the series of sine of x. So we're going to look at sine of x, but instead of x, we're going to use t squared. So our series starts with x, so we're going to go ahead and substitute in t squared. Plus our second, or minus, because it's alternating series. Or alternating series. Minus, so we have our odd intervals. So we have x cubed over 3 factorial. Then I'm going to have x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And then we keep going on with that. I'm going to plug in t squared for all of these. And now all we're going to do is simplify. So t squared stays the same, minus t squared raised to the 3rd power. So I have a power raised to another power. We're going to multiply those exponents together. So we have t to the 6th over 3 factorial. T squared to the 5th power, multiply them together, we get t to the 10th over 5 factorial. T to the 14th over 7 factorial, and that's going to go on forever. So we didn't necessarily need to do a ton of stuff. We can kind of substitute what we want into our function and then simplify as we go. So if we can remember the base functions, then we can substitute to kind of get everything else that we want. Okay, so let's look at the power series representation for e to the x squared. So at its base, we're going to, instead of doing e to the x, we're going to say e to the u. So u is going to be what we want x squared to be. So its original at its base, we have e to the u power. This is 1 plus whatever our variable is to the first, plus our variable squared over 2 factorial, plus our variable cubed over 3 factorial. This is the one where it's every single one more exponent, 1 more factorial. This goes all the way up to u to the n over n factorial. Okay, so now what I'm going to do is instead of u's, I'm going to put x squareds in there. So I have e to the x squared. 1 isn't a u, so we're leaving it alone. Everywhere there's a u, I'm just going to put parentheses for now, and I'm going to fill them all in with x squareds. Okay, so everywhere I have a parenthesis, I'm going to put an x squared. X squared to the n, x squared cubed, x squared squared, and x squared. And then all I'm going to do is simplify what we have. So 1 is our first term, x squared is our second term. X squared squared, so we have x to the 4th over 2 factorial plus x to the 6th over 3 factorial. And we're adding every term together until we get to here. So x squared to the nth power, so 2 times n, so we have 2 to the n factorial, 2 to the n power, and we're dividing by n factorial. And we can kind of see that pattern. So I have my denominator, and then if I times my denominator by 2, that's going to give me my exponent number. So 2 times 2 is 4, 3 times 2 is 6. If we kept going, 4 times 2 would be 8, which would be the next exponent. So this is what our function would look like, and if I needed my first 3 terms, I have my first 3 terms, and I have my general term. So all we're doing is using those base functions to help us write more complicated functions.